So while we are discussing today analysis of quality control data, and more specifically, we will discuss this fault prediction in case of significant noise and imbalance. And the scope of today's presentation is that I will be discussing the methodology that we have developed to classify noisy and imbalanced data. But before presenting that methodology, I will present the real life case or real life problem on which we are working, and that's the motivation behind that methodology. So this is the diagram from our industrial partner. This is the manufacturing process of our industrial partner, and they are world leading producer of frequency converters. And for the sake of this presentation, let's consider that they have a product that contains the different electronics parts, and they are producing these parts in different manufacturing lines, and then at the end they are assembling on the unit assembly stage. And all these parts, it's a very complex product, and all these parts are differently manufactured on a different production line. And the idea in this project is that we would like to predict the last stage quality control status by using the historical data. So from the previous slides, what we've got, the basic 2 points is that we have a multi-stage manufacturing process, and each product is actually a combination of different other products that are manufactured or produced on a different through different production processes. And each product inside the main product have a different use, purpose, and different type of a quality control. That means due to that reason, we have a heterogeneous type of a data that for each sub part of a product. And in this project, our objective is that if we can use these heterogeneous data streams in order to predict the last quality control stage. In that case, I have used the green color for the last quality control stage, and this is called in their production process that the unit test. And I will go in the next slides. I will tell you that why we are interested in the unit test stage prediction. Why not in the other, maybe the high power test or maybe other test stages? But at the moment, let's consider this is the most important stage that they want to predict, and strategically they will save a lot of resources and a lot of money if they can predict this QC four stage. So what will be the gains that they will have? Number one, it can be a resource optimization if they can predict the QC4, or it can be a time optimization as well. And another thing that we can have, if we'll be able to have a predictive model that predict the last quality control stage. In process of getting this model, we will have a lot of process understanding as well. So as any data mining project, we have started with the exploratory analysis, and just to see that what exactly the different quality control stages are producing. So it is just a categorical representation of the end result of the quality control stages, which is in the form of pass, fails, and repairs. And we just want to see that how each product, how it is performing on a different quality control stages. Let's say QC1, QC2, 3 or 4, what exactly the numbers for that, and how that product is performing on that particular quality control stage. And what we have seen on 2 different data sets is that if we'll just focus on the last quality control stage, that is the variable, that is the stage that we want to predict, the probability of failure is around, here it's around 1%, and here in the data set 2 it is around 3%. Which is a very small number, and it makes perfect sense because if we'll see each subproduct has its own quality control stage, and then after that it's coming to the other quality control stage, and then it is going to the unit assembly and then assembled together, and then it has again the quality control stage. So it is a quite optimized process, and it makes perfect sense if we have a very small probability of failure at the last stage. And but this is a problem for us if we want to predict the last quality control stage, because if we only have around 1% or 3% of data for a one class, which is in our case is a failure or repair, instead of 99% or 97% data for the other class. So that is a kind of a significant imbalance between two classes. One class has a very small number and another class has a very large number. So if we'll use the standard classification methodology, they will not give us the desired answer. We'll discuss this in the next slides. So with this motivation, we have started working on a methodology which can deal with all these problems that we have in our project. And we have started with looking on a very simple problem. If someone is working in classification in a data mining field, this problem one is a very well-known problem that is called XOR problem, where you can easily, with the human eye, you can find a good separator. Not the best one, but the good separator is easily is a very easy job. And then if you go to the problem 1 to problem 2, then we have more noise. The problem or the imbalance is kind of the same. The number of reds and the number of blues, the difference between the reds and blues are kind of the same, but there is a bit more noise. So it's in that case, it's very difficult with the human eye to find the good separator between blue and red. Then if we'll go from problem 2 to problem 3, problem 3 is we don't have that much noise in problem 3, but it is a completely non-linear type of a classification. So a linear classifier cannot classify these blues and reds. But if we'll go from problem 3 to problem 4, this is the case that we have in our manufacturing process, where the one class is significantly lower than the other class. So in that case, the red ones, the smaller class is exactly between 1% to 3% of the total data, and the blue class, which is the big class, it is around between 97 to 99% of the whole data. And if we want to use any classifier or any existing classification methodology, it's very difficult to classify reds and blues by using the existing methodologies. There are some methods to deal with this type of a problem. Mostly people use the different resampling methods or feature extraction methods, that is like kind of a filters or the wrapper techniques, in order to deal with these type of problems. In the resampling, there are different methods. Some people prefer to use the oversampling or of the lower class. For example, in that case, they will oversample to the red ones equal to the blue ones, and then they will use the standard classification methods. Or they will use the undersampling. For example, they will undersample the blue class equal to the red class, and then they will use the standard classification methods, or a different way. Or in the feature extraction, people use principal component analysis or some other pre-processing methods in order to deal with the classification imbalance classification problem. Or the other type of methods that are normally used in the literature are the boosting methods or the cost sensitive methods, where you put some cost to the lower class or the upper class, and then you try to optimize your objective function on the basis of the previously decided costs. So these are the existing methods at the moment in the in the literature. But what we have proposed is another way of solving the problem, which is a kind of a so-called way of doing using the existing methodologies and trying to optimize by using the evolutionary principle of optimization. And let me explain our methodology. It is very simple and intuitive. But we have decided that if we will be able to, for example, if we have this problem and we will be able to partition our space into with a certain rule, and we will take all the partitions that are having more reds into a one bin that will be called as a red bin or the failure bin, and the other should go into another bin that will be called a blue bin, so that we will be able to make the classes that are make the classes, and we can say something about that particular bin have a more probability of failure or have a more chance of going to a particular class or something. So as I said, that the idea is that we want to partition our information space, and then we want to have a comparison criteria to select the different partitions into two bins. It can be blue and red bins, or can be named anything. But then the challenge that we have is that, number one, how should we partition our information space? We have proposed a Voronoi tesselation methodology to partition our information space. It's due to the nice probability of Voronoi tiles, as each Voronoi tile is a convex hull, and it makes very easy to the some of the mathematical properties of Voronoi tiles make it very easy, or make it more reasonable to use for the classification purposes. And then the next challenge that we have, if we will partition our tiles, then we have to find a criteria to select the tiles into the blue bin or a red bin, or we need to have a sound statistical methodology or a mathematical methodology that will decide that whether that particular tile or the particular partition will go in a one bin or another bin. In order to do that, we have used the properties of binomial distribution, and we have developed a objective function that is based on the binomial distribution and the confidence interval of the binomial distribution. And in the later slides, I will present that objective function as well. And the third thing that we need to do is that, okay, we have the partition, we have the objective function that will decide whether a particular tile will go in a one bin or another, but this selection of tiles itself is a combinatorial problem. For example, here in that case, let's say we have around 30-40 tiles, but it can be in a real life problem, it can be 1,000 tiles or more than 1,000 tiles. Then putting these 1,000 tiles and into one bin or in a second bin is a combinatorial problem. So we have to come up with the solution or with a smart solution to select these tiles as well. So for that purpose, we have used genetic algorithm, that is a evolutionary type of a algorithm. That so the whole idea is that we will learn from our previous iterations, and we will try to optimize in the evolutionary principle. So let's go through the different parts of the methodology as I explained. So we will first randomly select the seed points for the partitions, and then we will use the algorithm called LVQ, the linear vector quantization or self-organizing map, in order to adjust our seed points for the to take care of the noisy part of the problem. And then these adjusted seeds will be the input for the Voronoi tiles, and we will tessellate, or we will partition our information space on the basis of the output of a LVQ algorithm. And then, as I explained, we will select the tiles by using the genetic algorithm and the defined objective function, that which tile will go to the red bin and which tile will go to the blue bin or another bin. So where the bins here are can be considered as the classes class 1 or class 2. So how the genetic algorithm works, it will generate it's just an example that I'm showing you these figures. It will generate a user-defined number of populations, and then it will calculate the value of the objective function for each population, and then it will select the best one, or on the principle of elitism, it will select the best 4, 5, or 10, that's the user defined number, and then it will go to the next iteration, and then it will select the best one from that iteration, and we will have this work on the user defined number of iteration, and at the end of the iteration we will take the best of the best ones, and that will be the solution for this problem. I'm not going into the details of the algorithm or into the details of the methodology or the mathematical aspects of these things. If someone is interested, they are welcome to go our website, Cambridge Service Alliance website. The working paper is there, and you can always contact us as well if you need more information regarding how we have implemented this methodology and the different mathematical or implementation aspects of this methodology. So these are the results that we have found for the problem. And this is the objective function. As I told, that I will discuss this objective function as well. This objective function is based on the confidence intervals of the binomial distribution. Why binomial distribution? As we know that we are working with the pass and fails, so this is dichotomous variable, and binomial distribution is the best representation of this type of a data. And then we have calculated the confidence interval instead of the point statistic, just to make our estimates more robust to the noise. And the third thing is that we are not comparing the point estimates, but we are comparing the different limits of the confidence intervals. That's again because we want to take care of the noise part of the problem. And then we are dividing this with the length of the confidence interval, so that if there is something, if one class has a small number of values, and then it will automatically take care, this normalizing part will automatically take care of these kind of problems. And we can see here in this figure that our methodology is classifying the red clusters quite well. So we have selected these tiles for the red bin and these tiles for the blue bins, and we can see that all the tiles that have comparatively more red, they are in the red bin, and the ones that are having comparatively more blue, they are in the other bin. But it's it's our explanation. So we really want to see that whether it is working reasonably well with the existing methodology or not. Then we did some experimentation, and we've compared this method with the existing method as well, and the next slides will have some of the results of this comparison as well. So previously I've presented just the results of problem 4, and this is the results of all these 4 problems. And we can see that for all 4 problems, our methodology is working reasonably well. And in case of a noise and in case of a real non-linear problem, we have our methodology is working comparatively well, but it's not like a best separation for example in this case, or for example in this case. And when we'll go to the comparison with the other existing methodology, we'll see that how our methodology is performing for all these 4 problems. And this slide is about the comparison of our methodology with the existing method. As we all know that in the classification literature, support vector machine, neural network, and k-nearest neighbor methods, they are some of the well-known methods of the classification toolkits. So we have decided to compare with these methods by defining the cost function in these methods, so that we can artificially take care the imbalance in that methodology. So we have compared all these 3 methods with our method, and the comparison measures that we have used for the comparison are these well-known measures such as markedness and F inverse, and we have used ROC space as well for the comparison. That will be a next slide. So in that case, we can see that for the markedness measure, our methodology is performing reasonably well in case of a problem 4 where we have a significant noise and significant imbalance. And same is the case for the F inverse measure as well. But our methodology is not performing well for the problem 2 and problem 3, where the other methodologies, especially the k-nearest neighbor methods, they are performing better than our methodology. And in problem 1, where we have a very clear classification and we don't have much noise, and the imbalance is also not as significant as we have in problem 4. So all these methodologies are performing equally well, and we have these values of these comparison measures kind of equal. And then we have another comparison measure, that is ROC space, very well known in the data mining community. And we can see that the same results, kind of the same results in case of problem 2 and problem 3. The other methods, they are performing well compared to our method. In case of problem 1, our method and other methods are producing kind of the same results. And in case of problem 4, we can see that the other methods, they are not performing reasonably well as compared to our method. Our method is having a comparatively very good results in case of a problem 4, where we have a significant imbalance and noise. So what we have proposed in this paper is a novel methodology to classify the imbalanced and noisy data. And this methodology is actually a combination of the existing methods, already existing methods in the literature, Voronoi tesselation, genetic algorithm, and self-organizing maps. They are already in the literature, but what we did, we have combined all these methods and proposed a methodology based on these methods by defining our objective function that performs reasonably well to solve our classification problem. And the one application, this methodology can be used in any field, but the one application that we have is the industrial manufacturing. And in industrial manufacturing, as in the most of the cases, the last quality control stage of the optimized quality control procedures and the optimized manufacturing processes, they have very low fault rate. But if there is a fault at the last stage, that is very costly, and then then you have to go back to see what exactly is the problem in the product. So as a promise in the beginning, that I will tell you why it is important in our case, is that because in case of our industrial partner, they are using a lot of time at the last stage of the manufacturing process, and they are also using a lot of costly equipment in case of last quality control stage. So if they are able to predict beforehand that this particular product be will be failed or will be passed, or with a certain probability they can say something about the characteristic of the product, then it will be really beneficial for them. They will save a significant amount of time, and they will save significant amount of resources as well. So in that case, so our methodology is able to predict the last quality control stage reasonably well compared to the existing methods, and it helps us to optimize the resources. It helps us to understand the different the dynamics of the process as well. So in that way, we have, by implementing this methodology in our industrial partners case, we have saved a reasonable amount of resources and reasonable amount of time as well.